and basics we are looking at the developments in classical thermodynamics. The foundation for all of the major results of classical thermodynamics are what may be called as the theory of calorimetry. It has the following basic ideas. First is homogeneity. There is no density or temperature gradients. That means the state of the system at any instant of time can be specified by specifying the total volume of the system, the body of fluid, and its temperature. So there is only one temperature associated with all of the body, and that is the same at all points within the body. Same goes for density. Then we have what is called as the equation of state, by which the pressure of the body of fluid is determined once I know the volume and temperature at any instant of time. Then we have the basic models for the work and heat, which are given by WR, that is the rate at which work is done by the body, is regarded as being given by the pressure times the rate of change of volume. On the other hand, the rate at which heat is added to the body is given in terms of this model. The point of the CV is the well-known heat capacity of a specific heat. Talking about the unit mass of fluid, and that would be the specific heat based on the mass of the substance. And this is the latent heat with respect to volume. That's a quantity that is not usually found or discussed in thermodynamic textbooks, but it is a major quantity. And in fact, while the heat capacity at least was in somewhat accessible to experiments, the latent heat was not. And Carnot explicitly says in his paper that one of his main aims to find out what type of a quantity this is, because he says that this is what may be called as a constitutive quantity. In fact, it depends on the particular material. The lambda V for one substance would be different. These are properties, just as the specific heat is for one substance would be different than of another substance. And it could be in general a function of the volume and temperature. There are three major constitutive quantities. One is the pressure, the equation of state that relates the pressure to the volume and temperature. So here. Then there are the two quantities in the model for the heating, namely the latent heat with respect to volume and the heat capacity. So as of now, thermodynamics finds a relationship between heat and work. As of now, there is no relation. We have a model for the work done by the body. We have a model for the rate at which heat is added to the body. Right? Nothing yet that connects the two. One of the main objectives of classical thermodynamics is to see how these quantities are related to each other. The major consequence of these axioms are that all the processes undergone by the body are reversible. In the sense in which we talked about yesterday, basic idea is that because of the specific model for the rate of work and the rate at which heat is added, right, the net work done in a process and the net heat added to the body during a process, they are determined by effectively, they are dependent on the path traced out by the process on the volume temperature quadrant rather than the specific details of the process itself. The details of the process are given, of course we can find the work and heat, but that is not needed. All we need is the path traced out by the process on the volume temperature diagram. Once we know that, the work and heat can be evaluated without knowing from which process the path came. So he pointed out that two processes with entirely different processes, if they are mapped onto the same path, then they have the same work and heat interaction. But the same token, if the reverse of the process is undergone by the body, the work and heat interaction, the reverse of the process will simply be the negative, the work and heat interaction in the forward process. All of these are consequences of the assumptions made here. Are there any questions on this? So now we'll go to the main results of classical thermodynamics. I'm not going to give detailed proofs or discuss these in detail. If you can understand this is the basis on which all the two laws of classical thermodynamics were formulated initially. That is sufficient for the purpose of this course. But I'll point out the two major, we call the cornerstones of classical thermodynamics. One has to do with the axiom of Carnot, the other has to do with the axiom of Clausius. Carnot's axiom dealt with the Carnot cycle, the cycle that is the name attributed to the cycle, which is attributed to him, it was first conceived by him. Whereas Clausius' axiom would refer to all cyclic processes. A cyclic process, is one in which the body begins at a particular state, and whatever it may undergo, it finally comes back to the same state here, which means the same volume and temperature. That's what we mean by a cyclic process. The Carnot cycle has the very easy to plot it on the temperature volume diagram. You might have seen the Carnot cycle in other diagrams, more common. Temperature volume is the original set of variables. In the temperature volume diagram, the main point about the Carnot cycle is that all the heat that is absorbed by the body during the cyclic process is done at one temperature, the higher temperature. All the heat emitted by the body is done at the lower temperature. So there are no heat interactions other than these two isothermal processes. So these two isothermal processes have to be connected by what are known as adiabatic processes. So I'll draw first, let's say body is at state A, then it absorbs a certain amount of heat at this temperature T plus. And now let me fix the temperature, the lower temperature, that is the temperature of the sink or the refrigerator. The sink, as it is called, one is the source and another is the sink. This is a heat engine I'm talking about, not a refrigerator. So heat is added, let's say the body absorbs heat and expands, it reaches a state B, and now it has to reach the lower temperature where it can emit heat, and this has to be done to an adiabatic process where QR is actually zero. That's the definition of the adiabatic process. So it will undergo adiabatic process and reach this temperature, and now it emits a certain amount of heat, right? And hence contracts. Typically, this assumes that lambda is actually greater than zero. That is typically the case. And so now has to go back to the final state for it to classify as a cyclic process. And that is accomplished by another adiabatic process. So these are isothermal processes. These are the Carnot cycle. With one Carnot did many things, but this one that is relevant to us here, that will lead to the first and second laws, is Carnot basically postulated the work done in a Carnot cycle is proportional to the heat absorbed at the higher temperature, that is Q plus. So this is the heat absorbed at the higher temperature. The proportionality factor is a function of the two temperatures. So that is a function of the two temperatures. In any Carnot cycle, the work is proportional to the heat absorbed, but the proportionality factor is not a constant. It depends on the two temperatures. vary with the temperature, and that is given by a function of T minus and T plus. Carnot himself did not find this function. He made several proposals for this function, but did not really come to a conclusion. But we know now that that function, what can someone give the accepted result for f? How is it related to T minus and T plus? It is ratio. It's not just the ratio. 1 minus the ratio of the two temperatures. We know that now. 1 minus T minus by T plus. But more importantly, or equally importantly, was Carnot made a universal component to this proposal. He said this function is the same for all bodies. So you take one fluid and let it undergo a Carnot cycle between two temperatures, and it absorbs a certain amount of heat. Then you take another body of fluid and let it undergo the cycle between the same two temperatures and absorbing the same amount of heat. He said the work done would be the same. That's a universal. Universal means the function is the same for all bodies, independent of the body that is used to. Because the body is the one, there is a body of fluid that absorbs the heat, then it undergoes an adiabatic process that emits heat to the sink and then comes back to its original state. The body goes through all these processes. So you need a body of fluid. So Carnot's one of the main components was that that function is independent of the agent or the body used to accomplish the process. So the basic idea why Carnot conceived of this, that he saw the temperature as sort of a potential for doing work. Just as he gives this analogy when he says a body that falls from a certain height uses potential energy. Right? This loss of potential energy can be used for converting into other types of mechanical work. Right? In the same way, by letting the temperature, effectively be transferred from the source to the sink through the body, where this drop in temperature, it can be converted to mechanical work. That was his main idea, the physical idea behind this. Now, Clausius' axiom was different. It applies to all cycles. The very famous that W is actually equal, is proportional to the heat, net heat interaction in all cycles. The difference between the Carnot's axiom and Clausius' axiom, as we see, this applies only to the Carnot cycle. This applies to all cycles. Here Q is the net heat interaction. Whereas here Q plus is only the heat absorbed by the body at the higher temperature. That's the only place where the body absorbs heat. So that's the heat absorbed by the body, whereas the Q there refers to the total heat interaction in the entire cycling process. Now there's an intermediate hypothesis that related to the ideal gas, and this may be attributed to Mayer and Joule. And that is that the pressure of the ideal gas is equal effectively to its latent heat. It's proportional to the latent heat. The proportional factor was denoted by J. Now, this is a somewhat unusual, since the books never discuss the lambda B. You probably might not have heard about this property of the ideal gas, but it can be shown that it is effectively equivalent to the other well-known relation for an ideal gas. The difference here in terms of the specific heat is a per mole specific heat. Then only you will have the universal. These two are related, they are in fact exactly equivalent. Right? But I'm not going to. So this is Mayer, Joule, maybe you can add Holtzmann. So This is the first property of the ideal gas. Now to make sense of, let's first look at this. From this, you can easily show, I'm not going to prove it. You can show that the latent heat is actually related to the pressure, the equation of state in this manner. And this is not to be confused with the chemical potential, but it's a universal function of temperature. This much follows from Carnot's axiom alone. So Carnot, as I pointed out, one of the main objectives was to find the latent heat, something about the latent heat, because it was not something that was very easily accessible to experiments, right? So he effectively found that by finding that the lambda is actually related to the derivative of the pressure with respect to the temperature, but to within a universal function of temperature, that he did not find that would mean that you should also know what this universal function is. So Carnot's axiom was not sufficient to find that function. He effectively found how the latent heat and the which appears in this model and the pressure which appears in the. So this is giving a relation between work and heat. It's translating the idea of Carnot in terms of what a heat engine can do, what are the factors that influence the work done achieved in a heat engine. And for that he chose a special cycle called the Carnot cycle. So that is idea of letting the temperature or the heat transfer from a higher temperature to a lower temperature body can be very easily conceptualized. Because those are the only temperatures at which the heat interactions take place. So within that context, he proposed this basic axiom. From that you can actually find a relationship between lambda v and the equation of state, which he effectively found. Now what about this? Carnot also made another assumption, which is often referred to as the caloric theory of heat, which would mean that effectively the Q equal to 0 in a cyclic process. This is the caloric theory. The body undergoes a cyclic process, then there will be no net heat interaction. This is clearly not correct, because that would mean if you combine that with the Clausius axiom, which means that no work can be accomplished in any cyclic process. This is not correct, but this was one of the other ideas used by Carnot which did not lead to correct results. But Mayer, Joule and all others were against this. They said it is not possible to get work from the process. Carnot basically said all it requires is to transfer the heat from a higher temperature to a lower temperature. There need not be a net consumption of heat in a cyclic process. So just letting the heat flow from a higher temperature to the lower temperature, we can accomplish work. There is no need for a net heat interaction in the cyclic process. This is directly contradicting this. And Mayer and Joule were opposed to this idea. But what do we replace it with? So both Mayer and Joule propose some kind of an equivalence between heat and work, some proportionality, but they were not always precise. And finally, this Clausius who came up with a correct principle of equivalence between work and heat. However, Mayer and Joule proposed the equivalence in a very special case where they effectively, you can say that in an isothermal process, this is the basis of all of this relation. In an isothermal process, they effectively said that work is proportional to, this is not a cyclic process, work is proportional to the heat for an ideal gas, as when they applied it. Now you can easily see for an ideal gas, we just equate the rate of work done, right? So I'll get dV by dt. Now this is all for an ideal gas. And at a constant temperature, right, this will vanish. And so I get J times, and so I can get that pressure. This is the basic idea of equivalence that they use. Neither Mayer nor Joule appear to have the correct principle of equivalence, they applied it not to a cyclic process but to an isothermal process. It's not a cyclic process. But fortunately they were correct, because if you restrict it to ideal gas, then it turns out to be correct somehow. Right? Because Joule did measure the quantity J through one experiment which involved an isothermal compression of air. So he clearly there applied this equivalence. But this equivalence is not true for all processes. It's not true even for all substances for an isothermal process. It's true only for the ideal gas. It happened to be true. They gave this important relation between the ideal gas. Now if I combine these two, let us substitute the lambda V. I can apply it to the ideal gas because it's a universal function. So we assume it's valid to the ideal gas. You get this important relation that the Carnot's function is actually inversely proportional to the temperature. Here we decided we take it as the absolute temperature. So the concept of absolute temperature itself took time to materialize. So if I combine these two, now I get the lambda V in its final form. So this is one of the major objectives of Carnot was finally accomplished. So the combined work of Carnot and that of Mayer and Joule for ideal gases. So what about Clausius' axiom? It immediately leads to the internal energy. For all those who think that it was Mayer and Joule who found the principle of conservation of energy, you might be surprised to know that it was first found by Clausius much after Mayer and Joule had proposed this kind of equivalence. But here, though, very easy to obtain the internal energy because this means that W into the JQ, that means PdV in a cyclic process. That's what W is. It is in a cyclic process. I now combine the two and bring this over to here and get in a cyclic process, in all cyclic processes. So the integral of this is a line integral, but it has to be carried along the cyclic process. This is equal to 0 in a cyclic process. So what can you say about this quantity J lambda V minus V dV plus Cv dt? So it is a what?
Conserved.
It is?
Conserved.
It's not a conserved quantity. Mathematically what it is? It has dV, dt and all, so you cannot say what quantity it is. It's a mathematical construct. I'm asking what you can say about this. It is what thermodynamics textbooks call an exact differential. Right? So what this effectively means is that this can be written as, let's say, dE, where E is a function of dt. So from that, I will get that dE by dV, constant temperature. These are some of the major relations of classical thermodynamics. That directly follows from Clausius' axiom. So when you integrate something, see, you have to understand, I just briefly explained. Some of you have asked me what textbooks of thermodynamics you should follow. But what is more important is what textbook of calculus that you should follow now to refresh all your ideas about calculus, the differential and integral and so on. Right? Whatever book you are comfortable with that you have used in your undergraduate, you should go back and review the basics of multivariable calculus. Without that, you will find the going tough in this course. Right? So, what we mean by when I write a quantity like this, many books call this a thermodynamics books would call it an inexact differential. There is nothing called an inexact differential. Either it's a differential or it is not. Right? So this may be in general integrate this over a certain path, right, the integral of that, right, how would you carry out this integral? Integral is usually carried out by, if R is specified on the xy plane, this is the path, let's say, I'm talking from here to here. If you want to do it, the simplest way to do it is to find a parameterization of the curve, and then I say that this curve can be parameterized as x equal to some x of tau, y equal to y of tau. Then I can write this as from 1 to 2, tau 1 to tau 2, a of x of tau, y of tau, by dx by d tau, plus the same thing for p. This is, you should review this basic ideas about line integrals. Now, if it's a general differential form, then the value of this integral will depend on the particular path. However, if this is a differential, which means let us say a is equal to df by dx and b is equal to df by dy, that means that a function f of x and y exists so that a is given by the x derivative of f and b is given by the y derivative of f, then that integral is very important in thermodynamics, because we always deal with so-called state functions over. So now, in this case, when it's not an exact differential, if I choose another path between the same 2 points, I can choose infinite number of paths. If the quantity a dx plus b dy is not an exact differential, then the value of the integral will depend on which path I choose between the 2 points. However, if there exists a function f so that a and b are given by this, then the integral, right, over any path will be the same. Whatever may be the path I choose, it will be the same. What will it be given by? If it is independent of the path, then what does it depend on? Depend on the end points, right? So this will simply become f of x2 y2 minus f of x1 y1. Right? So here we are saying that, so what it means is that if now I carry out the cyclic path and carry out, suppose let's say I take this path, which is now a cyclic path. So I start from 1, I go to 2, and then I come back to 1. But I can do it any number of times, the answer will be the same. Right? If I come back to it, right, then you can clearly see that for a cyclic path, any cyclic path between the 2 points, this is simply equal to 0, because I have come back to the same point. I can go wherever I want, I come back to the same point. The same relation holds. The integral is given by the difference of the function between the 2 points. Now the 2 points are the same, so the integral will be 0. This is actually the converse of what I am using. What this says is that if whatever the quantity that is within the integral is an exact differential, then, right, you can show that the integral of such a form over a closed path is 0. What this uses is that for every cyclic process, right, the integral of a certain differential form is 0, which is what Clausius' axiom implies. Then it can also, you can prove the converse. There are certain constraints about the nature of the region, connected region and so on. We won't get into all those technicalities, but basically the converse of that also holds with some restriction, that if I know that for every cyclic path the value of a certain integral of a differential form is 0, then I can conclude that that differential form is an exact differential. It's actually a differential. Nothing like an exact differential is an exact differential, right? So then you don't even call it a differential. So what does that mean? That means that x is a function f. Here I am calling it E, the internal energy, such that dE by dV will be given by this, dE by dt will be given by this, right? And then you can also infer from the equality of the mixed partial derivatives that d by dt is equal to d by dv of because this is dE by dV. So what I am showing here, or what I am using, is the fact that d squared E by dE, this we all know. Doesn't, again, there are some properties of the function has to satisfy, but for our purposes, we can take this as given that it doesn't matter which way which order in which you do the second derivative, right? Whether you differentiate E with respect to B and then D, or D and then B, the two quantities will be the same. If I use that, then I will get this. We'll see what the utility of that is. But first of all, you can now see this major result of classical thermodynamics is the internal energy of an ideal gas depends only on its temperature. This is actually a consequence of the first law effectively. We take it as given to us. So if I now impose this relation between the pressure and the latent heat of an ideal gas, then I get that the ideal gas dE by dV is 0, so EIT is a function only of temperature. Then what? Then we have here the lambda V appears here and P also appears. So if I sort of substitute, I guess, for dP by dt from here, so if I combine now these two, I'm not going to go through all the details. If I combine these two, then I can show another important. Where is the first law in this? First law, let me derive the first law, dE by dt by A, right, dE by dt. Now I am regarding E as a function of time, right. Here I know that E is a function of volume and temperature. I have proved that from Clausius' axiom. But I know that in a process, and that's what you have to define. This is very important in all of the codes, because the same function will be expressed in terms of different sets of variables, and you should be very clear, right, what is going on, right? Because here I have started out by saying E as a function of B and T, so here suddenly I am saying E is a function of time. Where does that come from? Well, in a process undergone by a body, right, we know that volume and temperature are functions of time. So since the internal energy is a function of volume and temperature, the internal energy will also change with time accordingly, right? So what I am doing really here is this. So I know the internal energy is a function of volume and temperature, but volume and temperature are internal functions of time. So you can ask whether the internal energy is a function of one variable or two variables. It depends. We're expressing it as a function of time, it's a function of one variable. We're expressing it as a function of volume and temperature, it's a function of those two variables. It depends on which you want to express it in terms of, right? So now I can apply the so-called chain rule, which says that this is given by dE by dV at T times dV by dV plus dE by dt. And this dE by dt is clearly J lambda V minus P times dV by dt plus this is ACV dE by dt. J is the Joule's constant. That was required. Now we don't use the J because the work and heat, it's just proportional in the cyclic process. It's not a function of temperature. It's a universal constant actually. Right, so it merely now serves as a conversion of units from calories to the modern work units or Joule. So as long as you express both the heat and work, they're essentially the same quantities. in the energy balance, right? So then you don't need the J, but this is the classical thermodynamics, a pre-classical thermodynamics, so it was very much needed in what that quantity was, because the heat in calorimetry was measured in units which we now call the calories, because the Joule unit was not yet established. But anyway, whatever units you choose, the mechanical units you choose for work, and the heat units or the calorie units for the heat interaction. So for that you need a conversion. That conversion factor was provided by J, and one of the major objectives of Joule's experiments was to find this quantity numerically. So now if I combine this, we get that this is simply J times lambda V dV by dt plus Cv dt by dt, right, minus dV by dt, which is clearly equal to what? What is lambda V? That is simply Q, and so this is given by A times QR minus WR, which you can immediately recognize as the first law of thermodynamics. So as of now, the form of the first law is restricted to the particular model. Within this context, only the first law and the internal energy was discussed. So the Q specifically refers to the QR, to this model. Now we don't regard the first law to be restricted to reversible processes alone. We apply it for all processes. We no longer even discuss the specific models for the heat. And for work in fluid mechanics, if you go to much more involved models which will involve the shear stress and so on, right? So, but this is the context in which it arose, and you can clearly see that it is Clausius' axiom, not the Mayer or Joule hypothesis, that leads to internal energy and the first law. What about the second law? As I said, if I combine this with this, these are the major relations of classical thermodynamics. This determines lambda V once and for all, without any ambiguity. This is another, we call it a restriction on the quantities, because as I said, right, the attempt of thermodynamics was to find a relationship between heat and work. In the context of this limited set of models, it's basically a relationship between these three quantities. This is one, this is another. It has all three quantities, right? If we combine these two, you will get another one, which is obviously derived from these two, and that is, you can show that we can show, if I combine relation 2 with relation 1, and this substitute requires some algebraic manipulation, so I am not going to do it, you can get this. Now what I do is look at this. This is d by dt of dE by dy. These are the same form, right? The same form, d by dE of dE by dt, but there is not dE but something else, lambda v by t. So I will now argue, again this is a converse. If I have this, then I get this. Conversely, if you have something like this, then you can propose that there exists a function s such that this is equal to ds by dv and this is equal to ds by dv. That's again part of the mathematics. We don't have to go into the details. Theorems exist in states, then that there exists a function s, so that this is given by ds by dv and this is given by ds by dt. So I can now write that out. This is clearly the entropy. Of course, modern treatments will begin with entropy and internal energy has been given to us. So you can see that this is actually used as the definition of the heat capacity. Here it arose through the model for the heat, but here without the J, this is used as a definition. An alternate definition is TdS by dt. These are major relations that have to be discovered. Now we use them as definitions. So you choose E and S as the starting point. It is now the logical thing to do once you have found them. Now again, I can see that ds by dt, if I do the same routine, ds by dt times dv by dt plus ds by dt times dE by dt, you can easily prove that ds by dt will be given by q. Yeah, this you take, what I want possibility is dp by dt appears, so there you put lambda v by t, right? And then you have this. If you do this, you will get this. It's very easy to prove that. I'm not going to prove it because it's not some major development for this course. You can easily prove it, right? I'm not shown exactly how it comes, but if you work it out, you will get it, right? Work it out, you will get it. The final result is this. I'm not going to go into the proof. If you're interested, you can prove it. So this now you can clearly see is the second law of thermodynamics, but only for reversible processes. Whereas now we accept the energy, the internal energy, and the first law as applicable to all processes. That's a generalization. When asked what is it that motivated, the founders to generalize, it may be the experiments of Joule, many of which involved even irreversible processes like friction and so on, created the idea that the first law is a more general principle, not just restricted to the particular context in which it arose. The second law cannot be extended like that. This is valid only for reversible. Of course, here both the first and second law appear as true results for reversible bodies capable of undergoing reversible processes alone. Now, how to generalize this for irreversible processes is still a topic that is not very well settled. There are many different proposals. Clausius' inequality, which we will maybe discuss later, doesn't really fully address the problem for irreversible processes. So this is what we have here as the conclusion of the development of classical thermodynamics, the discovery of the internal energy and entropy, and the first and second laws of thermodynamics as proved results for bodies capable of undergoing reversible processes alone. Are there any questions? We will now see from now on, we'll forget about the lambda v and so only quantities, the lambda v will go out of the picture and we'll formulate this whole thing so that it involves just the E and S, and we'll see what to do with it and how it is related to the major part of this course, right, in tomorrow's class.